everyone, welcome to GemChem. Now today's video is on solid state and this is a new topic right now in the channel. So before starting, if you have not watched the previous videos on BSc Physical Chemistry, you can watch it on the channel. I will give the link in the description box as well as the I button present above this video. Now let us start today's video. Now first we will deal with laws of crystallography. That is first law of crystallography, Steno's law. It states that there may be different external shape or habitat, but interstitial composition of them with same substance is same. That is, the crystal may be looking different from different phases, but the composition within the crystal remains the same, whether it's the angle, whether it's the length, whether it's the side length or unit cell length, it remains the same. To simplify it, we can state that the angles between the corresponding faces of various crystals of same substances are constant. That is, suppose this is a crystal and this is our angle, that is alpha. So, if the crystal is found in some part of the country and again it is found in another part of the country, though it looks different from outside, but the crystal angle remains the same. This is important. Here also the crystal angle will remain the same for this particular crystal. Now the measurement of angles forms an important part of the study of crystal. So this crystal angle measurement is important for this case. So the instrument used for this is goniometer. This is important. Now we see what do we mean by interstitial angles. It is the angle between normals of two adjacent planes intersecting one another. That is, basically it is the angle between the two planes placed side by side. This is the interstitial angle. Now what is the lowest structural motive of a crystal? It is a unit cell. The lowest structural motive or the unit, which is the simplest unit of a crystal, is known as the unit cell. Now on division of two crystals of same external habit, we get such structural motive which is known as unit cell. Now we see this is the second law of crystallography, also known as Haüy's law of crystallography. Now this states that for all crystal system there may be considered a set of unit vectors along three non-coplanar axes for any standing plane, such that any naturally occurring plane must have ratio of intercept with respect to vector, which are the integers or non-integers. That is, basically it states that there is considered planes, that is x, y and z axis is considered. These are non-coplanar axes which are present in three perpendicular directions and the planes of the crystals are being placed and we get a ratio with respect to the intercept. Suppose this plane, that is the green one, makes an intercept with z axis at L dash, whereas for y k dash and for x it is h dash. So this ratio is being considered as Weiss's indices. This is the cell length, that is the length of the cube or the type of unit cell in different axes. So this is A, this is B and this is C. So we consider it as h dash, that is intercept divided by the cell length. So this is the Weiss's indices. H dash by A is to K dash by B is to L dash by C. Suppose we have H dash, that is the intercept, as 2A, K dash as 3B and L dash as 4C. So what will be the Weiss's indices? So it will be H dash by A is to K dash by B is to L dash by C, and on putting the value 2A by A is to 3B by B is to 4C by C. So on cancelling these we obtain the value to be as of Weiss's indices to be as 2:3:4. Now if any plane is parallel to axis, it will have an intercept at infinity. Now ratio of rational intercepts, this is another form of Haüy's law. It states that for every crystal system there must be a set of non-coplanar axes. The ratio of reciprocal intercept with respect to axis is small integer or ratio of small integers. Now what is Miller indices? It is just the inversely proportional to the intercepts of that faces on chosen axis. If this is our Weiss's indices, then the Miller indices for this, that is mi for this, will be equal to 1 by 2 is to 1 by 3 is to 1 by 4. If we take the LCM, we get it as, the LCM will be 12, so we get it as 6 is to 4 is to 3. This will be our Miller indices, right? Now we see the next topic, that is lattice points. Points arranged in space with equal distances from one another to make the lattice is known as lattice points. So we can add the point to make the lattice, right? Now it may be an atom, molecule, ion or center of gravity of a molecule, and we can denote it as points, right? So if this is suppose a lattice represented by the lattice points, and suppose we consider this to be our unit cell. So here it has 4 lattice points in it, but it is also shared by the other parts. So this lattice point is being shared by 4 unit cell, right? Now we will consider about the unit cells. What are the unit cells? In 2-dimensional, we can consider unit cell as 2 types, that is primitive and non-primitive. All lattice points when lies in the corners of the unit cell as shown here, that is all lattice points are lying in the corners of the unit cell, then the unit cell is known as primitive, and non-primitive is, in this case, lattice points can lie along the corners as well as occupy the center. Now what are the parameters by which they are represented in 2-dimensional? AB, that is the length of the sides and the angle between the sides. There are 5 types of unit cell in the planar lattice, and we will see that thing. Now first we consider first type, where the lattice points are being placed in proportion like this, and we draw it as this, where A and B length is similar, that is A and B length is similar, and angle is 90 degree. A equal to B and angle equals to 90 degree. In the second case we consider difference in length, where here in this case A and B, A is smaller than B, so we write A not equal to B, whereas the angle remains as 90 degree, right? In the third case we consider A, B same, but the angle becomes different. So let us see this one, that is if we draw a hexagon like this, suppose we consider this is the point and we draw the hexagon like this. By joining these lattice points, then A equals to B, and this is the part, that is this is A and this is B, but the angle becomes equal to 60 degree, right? So here this is A and this is B, okay. So here the angle becomes 60 degree. Now for the next lattice, that is if lattice points are placed slightly slanting, then the angles changes, right? So in that case we can write it as, if this is like this and this is A and this is B and the angle is not equal to 90 degrees, so we can write it as A equal to B, whereas angle is not equal to 90 degree. And another case like this, if we consider, here in this case all asymmetry occurs, right? So in that case, here we consider A not equal to B, whereas the angles are also not equal to 90 or 60. There is total asymmetry in the last one. So we have obtained 5 unit cells in 2 dimension, right? Now we will see for the 3 dimension. Now unit cell in 3 dimension is being represented by A, B, C, and the angle between A and C is considered beta, between A and B considered gamma, and between C and B considered as alpha, and this is important. Now we have written that parameters used for representation is A, B, C, and alpha, beta and gamma. Now from these parameters, using these parameters, by making them equal or unequal, we can get 7 types of crystal system. Now we will see the 7 types of crystal system. Now first one is triclinic. In this case, all the asymmetry occurs together. That is, no sides are equal, no angles are equal, and the example of triclinic is this one. We need to remember this chart very carefully, as exam questions come from here, one at least. So for next one, it is monoclinic, right? So here there is no symmetry in sides, whereas angle, these 2 angles are same but gamma angle is different, and the example is this one. For orthorhombic case, it is also same, there is asymmetry in sides whereas the angles are equal, and these are the examples. Now see for trigonal, same thing, but here sides are equal whereas asymmetry occurs for this one. Angles are equal but it is not equal to 90 degree, and calcium carbonate and calcite are the examples. Now we see for cubic, there all symmetry occurs. Here all asymmetry occurs, here all symmetry occurs. And then tetragonal, where we see that there is one asymmetry in the side whereas the angles are equal, right? And these are the examples. And the last one is hexagonal actually, and we see that here asymmetry occurs for C, and here the angles are 90 degree and gamma equals to 120 degree, and these are the examples. In this chapter, this chart is the most important thing, which is important in respect to questions. So now we will see the structures. Now see, this is simple cubic, this is tetragonal, this is orthorhombic, this is hexagonal, rhombohedral, monoclinic and triclinic. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.